Okay, so for question 4, we are asked to calculate the linear density expression for BCC 111 direction and planar density for BCC 111 plane. Okay, so let us start with drawing our 3D projection. We have our z-axis, y-axis, and x-axis, and 8 corner atoms again. So we have 8 corner atoms, but for body-centered cubic, as the name implies, we have one atom sitting at the center of the entire structure. So first, let's calculate the linear density expression. So linear density for the 111 plane is asked. 111 direction, sorry. So the 111 direction is the body diagonal, and we show it as such from going from the origin to the point 111. This is our 111 direction. And the linear density expression is going to be length occupied by the atoms divided by length of the direction in question. So if we inspect the 111 direction here, at the origin we have one atom sitting, then at the center one atom more, and then at the 111 point here one more atom. So between these two points we have our 111 direction. This is R, this is 2R, and this is R. Now for body-centered cubic, the atoms touch on the body diagonal. So if you calculate the length of the body diagonal from here, so we have edge of A, then we have the face diagonal A square root 2, and these are perpendicular to each other in 3 dimensions. A square root 2, then this is going to be A square root 3. Then the linear density expression for 111 is going to be length of the atoms 4R divided by A square root 3. However, we know A square root 3 for body-centered cubic structure is 4R. Then this is 4R divided by 4R. If you simplify this, you will get 1. So the entire 111 direction for the body-centered cubic structure is filled with atoms. If you observe the structure from the 111 direction, you will see nothing but the atoms. It's entirely filled, and this is the most densely packed direction for BCC. And most densely packed directions also have a special name. These are called slip directions. Okay, so then let's calculate the planar density expression for the 111 plane. Let's draw another diagram here. Okay, we have Z, X, Y, the corner atoms. Then we have one more atom at the center, and we need to draw the 111 plane. Take the reciprocal. The indices show us that it must cut the cube at the corners. Then we draw it. Now at first thought, from the 2D projection, we can think that, or we may be fooled that this body atom is included in the 111 plane, that the 111 plane will cut the center of the body center atom. However, if you inspect it in 3 dimensions, either by drawing in a 3D modeling program or simply by searching on the web, and this is also included in recitation slides, this atom is not inside this plane, and so if you draw the 111 plane, there is no center atom here. It's empty because it doesn't cut the center of this plane, of this atom. So again we have an equilateral triangle with side length a square root 2 here. And these are the area occupied by the atoms. The linear density expression is going to be the same. N atom times A atom, area of the atoms, divided by area of the plane. Okay, let us calculate that now. So we have 3 atoms sitting at the corners, 60 degrees, 60 over 360. 1/6 of the atom is inside the plane, and the area of an atom is pi r squared. Now the area of the plane is again calculated by the regular equilateral triangle area expression, where this x is a square root 2. So a square root 2 squared square root 3 divided by 4. However, for body center cubic structure, we have a square root 3 equal to 4. This is for body center cubic structure. So A is going to be 4 divided by square root 3r. Substitute this squared over times square root 3 divided by 4. So that gives us a complicated expression for the area of the plane. So the planar density of 111 plane in BCC is going to be 3 atoms, 1/6 of it is included, times pi r squared divided by this whole expression. So 16 times 2 r squared divided by 3 times square root of 3, this whole thing divided by 4. I hope it's clear how we got this expression. If you simplify this, you will get pi r squared divided by 2 divided by 8 square root 3 r squared divided by 3. Simplify that even further. So 3 pi divided by, let's see, 16 square root of 3, I think it's the expression. That will give you 0.3401. I might have made a mistake in the simplification, so I'm sure this is the correct result, but I'm not so sure about this one. But as we can see, 34% of the 111 plane in BCC is filled with atoms. In contrast to FCC, as we calculated, 91% of FCC 111 plane is filled with atoms.